4 years. 4 years. I was MENA for 4 years.
¿Sí? Estamos en vivo.
Sí, listo. Pero me avisa. ¿De una?
2 minutos. Comenzamos a las 4 puntos.
Apenas ya me enviado.
Le recordamos al público asistente no descuidar sus objetos personales. De igual manera, le recordamos que está prohibido consumir alimentos y bebidas en el auditorio. Gracias. Le recordamos al público asistente no descuidar sus objetos personales. De igual manera, le recordamos que está prohibido consumir alimentos y bebidas en el auditorio. Gracias.
Would you like your pointer? And it has automatic.
Yeah.
It's supposed to work.
It's supposed to work.
Les doy la bienvenida a nuestro evento, a la charla del doctor Gregory Bobinger. Entonces, que es un honor para nosotros tener al profesor Bobinger acá con nosotros. Voy a ser muy breve, me pidió ser breve, porque le da vergüenza escuchar tanta cosa importante que ha hecho, pero voy a hablar un par de cosas. Él acabó la triple carrera en la Universidad de Purdue, que es física, ingeniería electrónica y filosofía. Él hizo el doctorado en MIT, el doctorado en MIT, el pregrado fue en Purdue, el doctorado en MIT, y después de un corto postdoc entró a los laboratorios Bell, que son unos laboratorios en Estados Unidos que realmente han generado el desarrollo de muchísima tecnología, en particular, digamos, la invención del transistor, para empezar. Entonces ahí empezó a trabajar con el desarrollo de sistemas de pulsación magnética, campos magnéticos pulsados, muy único el sistema. De ahí entra ya él a trabajar en Los Álamos, en el Laboratorio Nacional de Los Álamos, en Nuevo México, y es reclutado como director, el segundo director del Centro de Magnetismo Nacional de Estados Unidos. Este centro se mudó de la Universidad de MIT a Florida. Entonces es una asociación está asociada a la Universidad Estatal de Florida, pero tiene participación del gobierno de Florida, también de la Universidad de Florida y a nivel nacional de la National Science Foundation, que le da financiación año tras año para continuar el desarrollo de estos campos magnéticos DC y también campos magnéticos pulsados. Entonces, el líder mundial en este campo y es un atractor de científicos de todo el mundo, ¿listo? Donde van 2,000 científicos a hacer experimentos allá y a usar estas facilidades, y él realmente está con ese propósito. También es un excelente científico, tiene más de 120 publicaciones en campos relacionados a fenómenos cuánticos emergentes. Bien interesante la charla de ayer de él. Y también es ya miembro de la Academia Nacional de Ciencias de Estados Unidos, que es una cosa bastante importante. Entonces tenemos a alguien muy chévere acá con nosotros. Entonces nos va a hablar principalmente hoy de las aplicaciones del laboratorio para investigación aplicada y solución de problemas. Entonces creo que es una buena oportunidad para todos para aprender, y no solo eso, para abrir la oportunidad para que científicos colombianos visiten el laboratorio. Muchas gracias.
Thank you.
Too long, huh?
Thank you very much. It's a great pleasure to be here at such a wonderful institution to talk about what we do at the National High Magnetic Field Laboratory, of which I am the director, and I'll be talking about many frontiers of high magnetic field research. One of the most exciting things about my job is the struggle to learn what the physicists and the chemists and the engineers, the materials scientists, the biologists, the doctors are doing in their research at the Magnet Lab, so that I can run around in front so it looks like I'm leading. So there's a lot of words, and I don't know if we can cut the lights at the front of the room, so it's a little bit easier to read. So there's a lot of words on this first slide, and you don't need to understand all of them now, but towards the end of the talk, I'm hoping you'll have some sense of what we're talking about. But high magnetic fields constitute a precisely tunable thermodynamic parameter. There are not many thermodynamic parameters. Temperature, pressure, the number of electrons in a material are several other examples. But the magnetic field offers many facets of research opportunities. So you can couple inside the sample to mobile electric charges, and each electron, in addition to having a charge, has a spin, which is our slang word for the magnetic field of the electron. So every electron has a charge and a spin, and the magnetic field couples to those. So you can immediately address all of the electrons in a given material. And that can tune electron interactions and quantum phases. I'll give examples. Everything in yellow are things that I'll give examples. You can probe electronic systems where you're looking at commensurability of magnetic field flux quantum with electrons. So let's say you have 3 times as magnetic flux quantum as you have electrons. You get nearly magical physics that occurs that won the discoverers a Nobel Prize. So by balancing the number of the quantized magnetic field with the electrons, you can drive new physics. I won't have time for that today, but we will talk about using the direction of the magnetic field. So magnetic field is not just a number like temperature, it's a direction. The magnetic field has both a magnitude and it points in a certain direction, and that can tune the science. We can measure molecular masses with unprecedented precision using a technique called ion cyclotron resonance. So you can actually spray a droplet of petroleum or any other complex fluid, and I'll give many examples of this, into a magnetic field, and because these molecules have an electric charge, they undergo an orbit, and all you need to do is measure the timing of that orbit, and you can measure time with great precision, and you can then calculate the mass of each molecule. So it's just like a family picnic. The heavy molecules move slowly, and the little children molecules move very rapidly. And by measuring that frequency, you know the mass of 100,000 different molecules in a given drop of your sample, oil in this case. We'll manipulate electron spins, but in this talk, I'll confine myself to discussing manipulating the nuclear spins. So if you look at the periodic table, everything in the world is made of those 100 or so different elements, and the nucleus is very isolated from the electrons. So it's like the sun at the middle of the solar system. There's a lot of empty space there. And we can also address the nuclear spins and cause them to do magical things that enable us to determine the structure of molecules. And so we'll learn structural and dynamical information of biological compounds, magnetic resonance imaging. You've all heard of magnetic resonance imaging, or MRI. Some of the older members of the audience may remember exploratory surgery, If you had a pain in your stomach and the doctors did not know what it was, they would perform exploratory surgery, which means exactly what it sounds like. They would cut you open with a knife and they would start exploring to see if they could find out what is wrong. So who would have thought that magnetic fields would replace going in and looking with your own eyes to give you a three-dimensional image of what's going on inside the body? And I'll give some examples of the cutting edge where we're advancing MRI science. And although I won't talk about it today, we can manipulate both electron and nuclear spins as a way to drive quantum information technologies like future quantum computing. So, what is the Magnet Lab? We have 3 sites, and the main site, the headquarters, are at Florida State University. We have the world's strongest magnetic field for a DC magnet. As long as we can pay the power bill, which can be $3,000 an hour, we can run the magnet at 45 Tesla. We need 4 million gallons, so 16 million liters of water to keep the magnet cool. We have 56 megawatts that come into that building. I don't know why my picture is up there, but if we can remove that, is there a way to get my picture out of there? Because the magnets are much more, no, here. And then also make that disappear. Gracias. Yeah, that's good. And then can you make this disappear? Super. And then our second location is, in fact, at, okay, now I'm frozen, but I just need to click, I think. Yeah, here we go. Our second branch, oh, sorry, I forgot to mention, behind what used to be my ugly picture is a beautiful magnet. This is for doing magnetic resonance imaging on mice and rats. It's the highest magnetic field for that. It's 21 Tesla. If you go to the doctor today, it's 1 to 3 Tesla. And so we can make high definition images. Our second branch is at University of Florida, where we also do magnetic resonance imaging. We have larger Bohr magnets there. And for physics, we can cool down the sample to 1 millikelvin, so 1/1000th of a degree above absolute zero, to study phenomena that exist in the absence of the noise and the signal disruption that's caused by higher temperatures. And then out in Los Alamos, we have a very large installation where we pulse magnets. So we don't try to cool them with the cooling water. We turn them on and off in less than a second, 10 milliseconds in this case, so that the magnet heats up, but not so far that the whole magnet melts. Because if we ran these magnets for more than 100 milliseconds, we would make 7 tons of molten copper. And this is the highest magnetic field that's ever been generated without blowing something up. So 101 Tesla. And the way we do that is we use the largest generator in the United States. If it were attached to a nuclear power plant to put energy onto the power grid, it would generate 1.4 billion watts. So this is 2/3 the capacity of Hoover Dam, which is one of the largest dams in the United States. And we have one generator that we use to power 1 magnet at a time. And to give you a sense of the size, these are not the shortest people at the Magnet Lab. This is a motor that has a shaft that's between 1 meter and 1.5 meters in diameter. And it has 500 tons that are rotating that we use as an energy source. So, to speed up a little bit, because that's kind of the general introduction, the Magnet Lab has a mission since it was founded in 1990 to operate a world-leading high magnetic field user program. And I'll tell you some details about that. We carry out in-house research in support of that user program. We maintain our facilities, we develop new magnets and scientific instrumentation. And finally, we conduct education and outreach activities, and this is one of those. We're funded primarily by the United States National Science Foundation. We also get quite a bit of funding from the state of Florida. We're a partnership of the 3 institutions I showed you on the previous slide: Florida State University, University of Florida, and Los Alamos National Laboratory. Now, The three major research themes that I'll talk about and that are on the poster outside are materials, energy, and life. This is an image of graphene. This is low-grade petroleum. And this is an image that actually came off of the Magnet Lab, where they're mapping the route of the neural fibers inside the brain using magnetic resonance imaging. Now, many of the world's scientific challenges are too big and too broad for one scientific discipline to solve. The MagLab's interdisciplinary research environment brings together scientists across the spectrum, from physics to engineering to chemistry to biology to biomedicine, who explore the fundamental questions about materials, energy, and life with the help of the world's highest magnetic fields. So what do we mean by high magnetic fields? So these are non-destructive magnets that are built for users to come to the Magnet Lab to use them. And these provide unique capabilities enabled by the unique research and development, the uniquely talented and technically diverse team. The key word here is unique. That's what our laboratory specializes in, things that just cannot be done elsewhere. And the experiments that I show you require these magnets to function. So the lowest field magnets are superconducting magnets, but we hold the world record. Every time you see a big circle, it's the Magnet Lab's world record magnet. So this is peak field by year. Right about in the middle of the chart is 1 million times the Earth's magnetic field. By the time you get to the top of the chart, it's 2.5 million times the Earth's magnetic field. So the lowest field magnets are superconducting magnets, but we have a 32 Tesla magnet, which is a full 4 to 6 Tesla higher than any other superconducting magnet in the world. The resistive magnets are the expensive ones to run. They're electromagnets, and we power those with our power system. The hybrid magnet uses both resistive and superconducting magnets to get to 45.17 Tesla, the highest DC field in the world that we've reached in 1999. 2 weeks ago in China, they announced 45.22 Tesla, which is 0.1% higher field. And we believe they'll be operating their magnet, as do we, at 45 Tesla. And then to go higher, you have to pulse the magnets. If you have a pulse that's 100 milliseconds, you can get to 60 Tesla. If it's 10 milliseconds, you can get to 100 Tesla. So to achieve these, in superconducting magnets, you have to have world-leading expertise in high-temperature superconducting materials and magnet technologies. To get this hybrid to work, you have to have 30 megawatts of electrical power and the invention of something called the Florida bitter plate to fabricate the DC magnets, and I'll show you what that is. And to get to this field, you need that 1.4 gigawatt generator and the invention of nanocomposites to fabricate the pulsed magnets. So the Magnet Lab attracts researchers from around the world. In 2021, during the pandemic, we hosted experiments by more than 1,600 users from about 160 institutions across the United States. The lines here in purple go to Tallahassee, the lines in blue go to Gainesville, and the lines in red go to Los Alamos. And from around the world, around 280 institutions from throughout the world. And we're very proud of the fact that there are national laboratories in Europe, in Japan, and China, and sometimes those scientists decide to come all the way to one of the Magnet Lab sites to do their research. Not too many researchers from South America, which is part of my interest in coming here. I'm pleased that in 2022, we will have a line going from Bogota to Tallahassee because Professor Geraldo Gallo did some experiments a few months ago at the Magnet Lab. Now, except for years with pandemics, when everything is unusual, every year, 20% of our users come from outside the United States. So even though this lab is funded by the United States National Science Foundation, they want us to have international impact. And about a quarter of our principal investigators, the leaders of the experiments, are the first time ever that they've been leading experiments at the Magnet Lab. So this is not a closed community. If you have ideas for experiments that need high magnetic fields, we can work with you to help you develop your proposal to apply for magnet time. And then it's provided free of charge. All you need to do is travel to the site. And indeed, we have some ability to help you with travel expenses. Our user program trains hundreds of postdocs, more than 500 graduate students every year. And every year, about 400 papers are published in the leading journals, proceeding of US National Academy of Sciences, the various Nature journals, Science Magazine. These are leading physics journals and some leading chemistry journals as well. And to give you a sense of the number of different disciplines represented, we have 7 specific facilities. I won't go through them all, but I'll mention a few of them in the course of the talk. But for now, just these are 7 different installations that specialize in different types of science. Our DC magnets and our pulsed magnets and our ultra-low temperature facility are mostly doing condensed matter physics with a little bit of chemistry and maybe some biology, biochemistry, and biophysics. But as you start to get to magnetic resonance facilities, these 4, whether it's electrons or nuclear or MRI or using ions, that was the spraying the petroleum into the magnet to measure the mass. These 4 facilities have much more chemistry here in blue and biology, biochemistry, and biophysics. So we span quite a range of academic disciplines. And if you go to our website, first of all, our central message, we would like to host your experiments at the MagLab someday. So this is our homepage. To request Magnet Time, you go online, nationalmaglab.org. It's the same for our same words for our Twitter and whatever else it is you kids do today. And then click on Request Magnet Time, which is up in the upper left corner on most pages, and that will get you started. We have quite a bit of education and outreach on our website. This is See Through Science videos. It's now in Espanol, and it is videos that give you a sense of what electricity and magnetism would look like if you could see electrons and see magnetic fields. So, how do you make a powerful DC electromagnet? Well, if you have a current flowing through a wire, there's a magnetic field that gets formed around the wire. Electricity and magnetism are interrelated to form electromagnetism, as it's known in modern physics. Well, if you want to amplify the magnetic field, you can concentrate it in the center of a coil. And so you get a stronger field in the coil of wire. What we do is we actually make our coil not out of wire, but out of these plates that we call the Florida bitter plate. And so the current goes around the plate, and you get a very strong magnetic field in the center. And I'll explain a little bit more how that works. But to give you a sense of the level of investment, to create 1,000,000 times the Earth's magnetic field in a DC magnet, you need at least 30 million watts of electrical power. We're in a city with 250,000 people. When we turn our magnets on, we're using about 5% the total energy that's consumed by the city of Tallahassee. You need an electrical current density going through this conductor that's more than 20 times the current density in the filament of a 100-watt incandescent light bulb. That heats the 2-ton magnet from 10 C to 40 C in 0.01 seconds. And it would melt the magnet in 0.1 seconds if there were no cooling water. And we require more than 8,000 liters of deionized water to pass through this magnet every minute. And deionized water actually corrodes the very magnet that it cools. So we're not very nice to these magnets. How do we make a disk into a solenoid, into a coil? We stack the bitter plates. So the electrical current will go around this one. It's isolated from the next one by an insulator, but there's one place where they touch, so the current can hop down, go around this one, hop down, go around this one, and that's how you make a coil. Now, we don't make it hop. This is an expanded view from the top. What we actually do is we stack them. So here's one plate. This is the expanded view you were looking at before, but in fact, the magnet, they're compressed so that they're in close, immediate contact with each other. So an actual stacked coil looks like this, and then you have to nest many coils like this to make a 41 Tesla resistive magnet or a 45 Tesla hybrid magnet. El Naranja here is for scale. I probably mispronounced that. This part, not that part. So, what's special about a bitter plate? They were invented in the 1930s by a man named Francis Bitter, who was a pioneer in generating high magnetic fields. He realized the disk was a good strategy. These big holes are for big bolts to hold the magnet together. The little holes are for the cooling water. The Florida Bitter disk, which we invented in the 1990s, enabled us to set new world records. And we turned these circular holes into these slots. So why would we do such a thing? Well, the forces are one of the biggest problems we have when we generate magnetic fields. Whenever you have an electrical current and a magnetic field, there's a force. And the force on these disks is outward, radially. And it's so strong that it exceeds the strength of most common materials. This is not plain copper. This is a nanocomposite of copper and silver. So the force that's on this inner layer under this old technology is not just the force that's generated there, but it's the force that's generated all in this region. And so the total force that's experienced by that part of the conductor is not just locally generated, but because there's current here and a magnetic field here, it's pulling outwardly. So this whole region of the magnet is pulling on this inner surface, which is not an ideal situation. So what we did instead is we made slots and we staggered them. So now you have a force out here, but you can pull on that outer part of the magnet, and it's like a spring. It does not transfer the force into the inner layer because the disk can now stretch. So now the stresses that this part experiences are much lower because they're only generated locally. So this was a huge revolution in high magnetic field generation that allowed us to get to much higher magnetic fields. And 4 of the top 5 magnet labs in the world now use this Florida Bitter technology. All right, materials limit our ability to make powerful pulsed magnets. What can you do? I've told you about DC magnets, now we're switching to pulsed. What can you do with 1 to 2 billion watts? Well, you can power the city of Los Angeles, which takes 2 gigawatts. This is a picture of Hoover Dam, one of the major sources of energy for Los Alamos. You can go back to the future. The flux capacitor, you may recall, is 1.21 gigawatts. I originally said it was 1.4. I said all of these are 1.4, and I had somebody in the audience in the questions section actually raise their hand to correct me. So everybody needs a hobby, I guess. Or you can pulse 1 magnet with this 1.4 gigawatt generator. You know, for a physicist, 1.21 equals 1.4, but not for everyone in the audience, apparently. So this is our generator. There's the 2 people for scale. We transfer 250 megajoules of energy from this inertial storage into a few tens of cubic centimeters of volume to generate a high magnetic field. This is the magnet, and that energy is equivalent to 500 sticks of dynamite. It's also equivalent to 500 Arequipe donuts. The energy in dynamite and food is contained in the chemical bonds. The number of chemical bonds per volume is about equal in these 2 different items. And so the total energy is the same. The nice thing about Arequipe donuts, in addition to the taste, is that it takes several hours to extract the energy. The thing that makes dynamite special is that the energy comes out in a few milliseconds. And our magnets are much more like sticks of dynamite than Arequipe donuts. So strength of materials limits the strength of the MagLab's magnets. I mentioned you have a coil of wire, and to make a higher magnetic field, just put more current in. Well, why don't we just double the current, and we'll get twice the magnetic field? I'll tell you why. Because the forces that are experienced by this magnet are explosive at the center of the coil, and they're implosive, they're crushing from top to bottom. It's exactly the same forces that are experienced if you crush a can of beer, or for your younger people who don't know what that is, a can of Coca-Cola. So how big are these forces? Well, if you swim underwater, your ears experience a compressive pressure. If you go 3.5 meters, your ears might pop. That's 0.4 kilograms per square centimeter. If you go in a submarine to 600 meters is trying to be crushed by 70 kilograms on every square centimeter. If you go to the ocean floor, 420 kilograms per square centimeter. So our 100 Tesla magnet experiences 14,000 kilograms per square centimeter. This is a piece of steel that's more than 1 centimeter thick, that used to be a cylinder, was ripped apart and bent into this shape by the magnetic forces alone. So we cannot use conventional steels. We have to use specialized materials throughout, and this is why we can't just double the current in order to double the magnetic field. We're limited by materials. So we're sort of have the same problem that these two spiders have at the bottom of a slide. They've built a web here, hoping to catch something big, as did we over here. And as they say, if we succeed, we'll eat like kings. And that's our philosophy at the Magnet Lab. If we're able to control these pressures, we can do wonderful new science. So we needed to invent and improve a nanocomposite to achieve 101 Tesla non-destructively. This is the magnet. Inside the core of the magnet is the inner coil, and the inner coil is made of these conductors, and it has the property, it's made of copper with niobium filaments, 5 times the strength of steel, conducts electricity like copper, and it bends into a coil for making magnets. There's no other material on Earth with these properties. And if you expand this picture, you can see that there's hexagons inside of hexagons. And finally, you get to the point where you can see the niobium filaments here. And those niobium filaments get to be so fine that they may only be 60 atoms thick. Now, why do we do that? How do these nanocomposites work? Well, you can take a paper clip or a piece of metal and bend it once or twice, and it's just fine. But eventually you can see cracks starting to develop, and then it breaks in two. That's called fatiguing the metal. Well, what this does is whenever you start to build a nano crack, it runs into the niobium, and it can't go any further. And so the nano cracks don't get a chance to join together to become micro cracks, which then would join together to become milli cracks, which then would become cracks, and the magnet would explode. And it would sound something like a stick of dynamite. And so pulsed magnets are applied metal fatigue. And the way we address that problem is the invention of these specialized nanocomposites. So materials limit our ability to make superconducting magnets also. So we're in the middle of a revolution. High temperature superconductors, new materials discovered in 1986, for which the discovery was awarded a Nobel Prize. We still don't know why they superconduct. Whoever figures that out will win a Nobel Prize. And if there's a key experiment that helps explain why they superconduct, that person will also win a Nobel Prize. Not that we're in it for the Nobel Prizes, but it's always nice to travel to Sweden in December. So these are the conventional superconductors that have been used for decades. In the middle 1960s, niobium titanium was discovered. It's used in all of the accelerators around the world. The big one in CERN, the Large Hadron Collider. It's used in all of the MRI magnets around the world, which is why they're less than 10 Tesla. If you want to go to higher fields, you use niobium 310. And the highest magnetic field there is 24.6 Tesla at a research laboratory in Japan. Well, the Magnet Lab made this leap by revolutionizing the use of high temperature superconductors. So we made as big a jump as has ever been made in the history of superconducting magnets, up to 32 Tesla. And we made a test coil that we put inside a resistive magnet that reached 45.5 Tesla. And that coil looks like this. The paper was written up in Nature. It was a Discovery Magazine top 100 advance of the year. Is there anyone in the audience who has a superconducting magnet in their laboratory? Anyone? Who can give the rest of the audience an idea of how big is a 15 Tesla magnet? Okay, so an ordinary 15, you have one. So show them how big your 15 Tesla magnet is, roughly. Right. So with high temperature superconducting materials, this is the size of a 15 Tesla magnet. This is not the actual one. I'm the director. They don't let me touch real things. This is made out of Teflon. But we were able to generate 15.5 Tesla with this coil, sorry, 14.5 Tesla with this coil, and we put it inside 31 Tesla to get a total of 45.5 Tesla. So that gives you a sense of just how revolutionary these materials are. Okay, so that's my only demo, so you can kill the lights. So what is it about superconductors that limit the magnetic field that they can create? Well, low temperature superconductors have hit a physical limit. The upper critical magnetic field, it's called, cannot be exceeded. So this is the ability to carry electrical current without any friction. And as you turn on magnetic field, going from 0 to 45 Tesla, the ability to carry that superconducting current drops to 0. This is niobium-3 tin. It's the most talented of the low temperature superconducting materials, but there will never be a niobium-3 tin magnet that exceeds 25 Tesla because it cannot carry superconducting current. What does superconducting current look like? The electrons actually, even though they're both negatively charged, so ordinarily they repel each other for special reasons, too complicated for this talk, but I could explain if there's a question. These electrons in some materials will pair up. They'll put their little magnetic fields, denoted by these arrows, in opposite directions, and they become a pair called a Cooper pair, named after Leon Cooper, who wrote the paper that described these bound up pairs of electrons. Well, they only exist here. If you have a strong magnetic field, you might imagine these are like the little compass needles. Eventually, both of these magnetic fields are going to want to line up with the applied magnetic field, and that breaks the Cooper pairs, which kills the superconductivity. So non-superconducting individual electrons live over here, whereas paired up Cooper pairs live over there. These conduct electricity with no friction, and these are just conventional metal with all the friction and the heating that's caused by that. So this limit is given by someone very powerful. It comes from the physical properties of the material. There's no negotiating with this guy. So that's the limit. Now, the same graph with the same axes, these are what the plots look like for high temperature superconductors. And there's a whole family of them. 3 of them have now been developed for use in magnets. These are almost horizontal lines. In fact, we don't even know where they lose the ability to carry superconducting current. And the amazing thing here is that whereas this limit is ultimately set by physical quantities we have no control over, this can be engineered. So pure YBCO, which is what this is showing you the current state of the art, but pure YBCO has a critical current density way down here at the bottom of the screen, which is useless for magnets. But engineers have been able to raise this critical current density up to much higher levels so that it's now feasible to make a magnet that's so much smaller than poor Paula's magnet. It's now much smaller to get high magnetic fields. And in principle, it might not just stop at 32 Tesla. We might be able to go to 100 Tesla. Now, we've still got to solve the strength problem because the forces are immense. But the sky's the limit as far as the behavior of this material. There's no limit from the guy upstairs. And so they've done this through incredible engineering. They put gadolinium in that helps align the crystals. They put in zirconium to make little nanorods along the C-axis, which pin magnetic flux. That's a lot of fancy words. What does it look like in pictures? Well, magnetic fields penetrate into a superconductor. This is meant to be the 2 sides of a tape that goes, it's kilometers long, going from way down there to way up there. And each, when you apply a magnetic field, you get vortices that penetrate into the superconductor. And each vortex has this little white region in the center it's not superconducting in the center. The superconductivity is in the blue parts. So as far as a conducting wire, it's perfectly good, but there's already some non-superconducting regions where the magnetic field has penetrated in. If you have a clean superconductor, the vortices typically form a hexagonal lattice, as I've shown here. But clean superconductors don't work as well for magnets. What you want to do is you want to put in pinning centers, which are defects that are either a point or shaped like a rod that don't allow the superconductivity to form in the vicinity of defect. So this material may be superconducting, but not where the red dots are. This material is superconducting, but not in the middle of the vortices. So what happens when you turn on the magnetic field on a dirty superconductor that's been engineered by these genius engineers? Well, the lattice, the hexagonal lattice, distorts. So the vortices shift because they want to line up their cores that are already not superconducting with the pinning centers that are already not superconducting, because then they don't waste any energy. And then once they're stuck on that pinning center, they can't move. And what I didn't tell you yet is when a vortex moves, it kills superconductivity. So the whole point behind hundreds of millions of dollars of research since 1986, when these materials were discovered, was to figure out how do you pin these vortices so they don't move. And they've moved that curve, as I showed on a previous slide, from way down here all the way up to there, and that's when you can start building amazing magnets. All right, so I'm faced with a little technical challenge here because I can see the entire slide except where it says Hablandos, which is where I chose to put my page number. So I have no idea what slide I'm on. I think I'm on 27. All right. I'll now switch from how we make the magnets to the research done using the unique magnets, instrumentation, and expertise. I'll warn you ahead of time, the first topic is physics, tends to be the harder one to understand. If you fall asleep, your neighbor should wake you up when we're done with the physics, because it gets a lot easier after the physics is over. But I wanted to talk about how physicists look at high temperature superconductivity. The engineers have already solved a ton of problems, and we're making magnets out of this material, but we don't even know why it superconducts. And my personal research is to try to understand why these things superconduct. Well, all of the materials of this particular family called the cuprates, because they have copper, they have a square lattice of copper atoms. Everywhere these lines intersect, there's a copper atom. And then you put one electron on most of them, but you remove about 16% of the electrons, and you get superconductivity. So if you have an electron everywhere, it's a magnet. If you have too many, if you remove too many electrons, it's non-magnetic and it's just an ordinary metal. But somewhere between about 8% and 25%, for some reason, the sample is superconducting. And this is temperature, and this goes up to much higher temperatures than have ever been achieved prior to their discovery. It increased this temperature at which superconductivity was observed by a factor of 5, which is why they're called high temperature superconductors. Well, I should also say, the pseudo gap, we understand the Fermi liquid, we understand this magnetic phase, we don't understand the pseudo gap. We completely made up this word because we don't understand what's going on, but that takes too long to say, so we call it the pseudo gap. Non-Fermi liquid just means we non-understand what's going on here. And I'll talk a little bit more about that. But there are other families now. These don't have copper, they have iron, and they superconduct up to about 55 Kelvin rather than 125 Kelvin. And these have a real magnetic phase transition. So this is a type of a magnet called a spin density wave. And over here, it's a non-magnetic metal. And where this phase transition is crashing down, instead there's a superconducting dome. It kind of looks like the cuprates, but it looks exactly like a material that's completely different. This is a three-dimensional compound. Cerium has electrons, it's way down at the bottom of the periodic table, so it has what are called F electrons. They drive around very slowly in the material. They're called heavy fermions because they move so slowly, but here there's a magnetic phase, an antiferromagnet as it's called, and in the late 1990s, a research group in Cambridge, England, was noticing that when they apply pressure, this transition was going down to 0, and they wanted to know what happens when you ask nature, do you want to be a magnet or a non-magnet? What's your answer going to be? Well, we have all kinds of theory that we understand about phase transitions that are driven by increasing temperature. We know why if you lower temperature, water becomes ice, or if you raise temperature, water becomes steam. What we don't know is if you're at 0 temperature, so there's no random thermal motion, but you change some other parameter like pressure or the number of electrons. What is it that creates the phase transition? There's no theory for that. Those are called quantum phase transitions. And it turns out that when you ask nature, do you want to be a magnet or a non-magnet, right at the point where you would have this quantum phase transition, nature decides it doesn't want to do either. Nature behaves like a 2-year-old child. It decides, I want to be a superconductor. We have now 2 dozen materials, 3 dozen, 4 dozen materials that show that when magnetism drops to 0, nature puts in a superconducting phase, right where we thought there would be a transition between a magnet and a non-magnet. We have no idea why, but this is the only rational strategy for looking for superconductivity. Find a magnetic phase that's dropping to 0 temperature as you vary a thermodynamic parameter, number of electrons or pressure, and when you get to the point where it should be going to 0, more often than not, you see superconductivity. In fact, now, when we don't see superconductivity, we think maybe the sample is too disordered and we need a higher quality sample. We've switched our thinking to what the heck is this doing here to why are we not seeing superconductivity? We have no idea why there might be this common phase diagram for superconductivity. Well, we go back to the high temperature superconductors. The magnetic phase transition is way over here. This pseudogap phase, there's something going on there. We don't fully understand it, but it does look like a phase transition coming down. And this material superconducts at temperatures that are more than twice any of those others, in some cases a factor of 100 higher temperature than those other materials I showed you. So maybe the differences here are the reason that these high temperature superconductors superconduct so well. So in the mid-90s, I started applying high magnetic fields to high temperature superconductors to peek behind the curtain, because high magnetic fields destroy superconductivity. You remember the slides before. The spins line up. So this is the gentlest way with high temperature superconductors to remove the superconducting phase, and the idea is to see, is there a quantum phase transition under the dome of these best of the high temperature superconductors. So we measured the number of carriers in the material as we changed the doping. So here, if you just look at 0 temperature, you can't take any data because it's superconducting. But if you look up at 100 Kelvin, so now you're way up above here, and you go across, the number of carriers in your material goes up as you increase the doping, which is donating carriers. Nothing mysterious there, but in order to know what's happening at 0 temperature, we have to apply 60 Tesla magnetic fields, and then we see something really bizarre. There's a peak in the number of carriers, and it's right near, in this case it's at 0.17, right near the situation where the superconductivity is best. So why is there something happening in the non-superconducting state right at the same doping where the superconductivity is best? This is either a clue to what's causing high temperature superconductivity, or nature is being really cruel and giving us a coincidence that has no physical meaning. But we think that this is a quantum phase transition, just like those other materials I showed you in the superconducting high temperature superconductors. There does seem to be a quantum phase transition under the dome of high temperature superconductivity in the cuprates. So this is more recent work. This name may look familiar. Professor Geraldo Gallo is here at Uni Andes. Her husband, Jose, is at Augusto is at Central. And this is data they took on a material that wasn't the original discovery, but it was one of the cleanest examples of seeing that there's other weird things happening in the non-superconducting state, right when the superconducting state is optimized. So this is resistance as you cool the sample down, and then it drops to zero resistance. That's the superconducting transition. But this is insanely linear. It's so linear that with PowerPoint you can do that, which since I was born before PowerPoint, I'm going to do twice. This is incredibly linear and goes up to insanely high temperatures until the wires attached to the sample melt. Nobody knows why this simple behavior occurs. So now we've got two strange things happening in the non-superconductor right when the superconductor is optimized. And one of the things that Paula Gallo and Jose Augusto discovered is that you not only have linear in temperature resistivity, you have linear in magnetic field resistivity at optimum doping. And nobody understands why that happens either. So there's still plenty of mysteries about what's going on. For an entire regime below 50 Kelvin and above 50 Tesla, the resistivity versus temperature is linear in temperature, and the resistivity in the same range in field is linear in magnetic field. All right, are there any other new mysteries in high magnetic field superconductivity? There are. There's been a material discovered in 2019 we call Lazarus superconductivity. Without going into a lot of details, there are 3 superconducting phases in one material. Here's the magnetic field going up to 60 Tesla, and all we're doing here is we're applying the magnetic field in different directions in the material. So how far down from this axis, and then how far around are we applying the field? Well, this phase is not so crazy. It superconducts at all orientations of magnetic field up to about 17 Tesla. That's what's crazy about it, is you have to go below 1.5 Kelvin to make it superconduct. So even though it's very weak against temperature, it's very strong against the effects of magnetic field. There's a second phase where you have to have the magnetic field within a few degrees of one of the axes. And then the third phase is called Lazarus phase, because the superconductivity lives, and then as you go to higher field, it dies, and then as you go to still higher field, it returns to life. Nobody has a clue what's the physics behind a superconducting phase that is so robust, it occurs at magnetic fields that should destroy the superconductivity for a superconductor that has to be 1 Kelvin to superconduct. Normally, if it superconducts below 1 Kelvin, less than 1 Tesla will kill the superconductivity. This superconducts at around 1 Kelvin, and yet it becomes a new superconductor at 40 to 60 Tesla. All right, that was the hard part. So wake up your neighbor if they're asleep. It gets easier after this. Now we're switching to energy. I've described already this technique for weighing molecules. This is what the data look like. Each one of these peaks is a different molecule, and its weight is given in Daltons. That's the number of protons worth of mass. So 500 Daltons is equal to the mass of 500 protons. But we're measuring, a complex molecule. It's just these are the units rather than kilograms. Well, we invented petroleomics, which is the quantitative analysis of petroleum. We can use mass to identify more than 100,000 different molecules in a single drop of oil. And if you know every chemical contained in petroleum, you can learn how to refine lower grade crude. We're running out of high grade crude. There's infinite amounts of low grade crude, but it's got sulfur, and you need to know the chemical formulas to know how to refine that crude optimally. You can also determine what's clogging pipelines. This is an actual pipeline that was clogged that we did the analysis on. It was thought that this clogging was made by very long molecules that had tangled themselves up. No, it's very short molecules that are attracted to each other through the electric field. You can track the evolution of oil spills. This is a lake with oil floating on top, and we can actually see what's happening to the oil as it's in the environment. We can discover what tar balls are made of. You would have thought that with oil spills being the problem they've been for decades, since we started burning fossil fuels, that we would know what a tar ball is made of. It was the Magnet Lab experiments in 2012 that determined. So they can resolve the difference of 3.4 millidaltons. So 0.34 the mass of a proton, they can tell the difference between 3 carbons and sulfur and 4 hydrogens, which weigh almost exactly the same. Well, this is the Deepwater Horizon petroleum. We got samples from the folks who were able to go down when that disaster was leaking. And then we looked at a tar ball that arrived on a beach in Louisiana. And this is the same range and mass. This whole range is just a few tenths of the mass of a proton. And you don't have to read all these. These are the chemical formulas of each one of these peaks. But this is the key. One would expect the tar ball to have fewer lightweight molecules because it was thought that the volatile molecules would have evaporated. The small molecules can go up into the atmosphere, leaving just the heavy ones behind. People thought tar balls were going to be made out of heavy molecules. Not at all. Instead, there are 3 times as many compounds over this same range of mass in the tar ball. And the reason is that sunlight and bacteria have oxidized many compounds. You can't read it, I don't think, but every one of these has oxygen in it. And none of these, with the exception of that one, have oxygen. So all of these compounds get oxidized. The atmosphere, the bacteria do their thing, and they oxidize. Well, oxygen is polar. It has an electric field. So the oxygen creates a force between the molecules. The molecules then stick together and become a tar ball. Nobody knew that tar balls were made of small molecules. Nobody knew that the oil pipelines were getting clogged by small molecules. So you're going to attack the problem completely differently than you would if it were large molecules. Well, we can also do green energy, not just polluting oil, developing biofuels with the help of high magnetic fields. So what we're trying to do here is make fuel out of pine chips. So we're converting agricultural waste into biofuel, and you need molecular level information to understand how to increase the efficiency to process the waste into fuel. Well, these are the molecules that are oily. They don't dissolve in water. These are the molecules that dissolve in water. If you're going to make a fuel out of pine chips, you want to know how many of these you've got because you want to minimize those. They're water soluble, and you want to maximize the oily ones. Well, we discovered a very nice correlation. If you just count the number of oxygen atoms per molecule, you have a pretty good idea whether it's going to be good for your biofuel or bad for your biofuel. This was work that was done in part by a high school student at the Magnet Lab. Biofuels are abnormally high in oxygen, which is polar, so it has an electric field that causes the molecules to attract to each other. Also nitrogen and sulfur, which is very difficult to separate in the mass as you measure the different compounds. The presence of these elements, oxygen, nitrogen, and sulfur, limits the analysis of biofuels using conventional techniques, and this work required high magnetic fields and this ion cyclotron resonance technique. Well, we've looked at what sunlight does to asphalt. It was thought that asphalt was made of these rings, benzene-like rings, if you know what those are, rings of 5 or 6 carbon atoms that make huge islands. And huge islands don't dissolve in water. So it was thought that asphalt was largely passive once you lay down the road, except for the holes that develop that you bump over. But in fact, asphalt has loads of molecules that aren't big islands. They're like archipelagos, where you just have one bond connecting. Well, the ultraviolet light from the sun can break that one chemical bond, and you get a lot of water-soluble compounds. These are the various spectra, but the point is that asphalt roads, as they age, are polluting the water around them. And so if you know every chemical structure before and after exposure to sunlight, you can answer important questions, such as what's getting into the river water. People did not realize that asphalt was this deleterious, and we still don't know how bad it is. We just know it's something that needs more research. Well, if you know every compound contained in water, you can answer questions of global importance in a time of climate change. We are partnered with Woods Hole Oceanographic Institution, as well as researchers in Canada, Russia, and we're collecting water from most of the major rivers that go into the Arctic Ocean. We're applying that to our ion cyclotron resonance technique. This is the tundra up there with permafrost. And what we do is we compare what's going into the river water in winter with what's going in the summer when the permafrost is melting. So we can tell what's getting into the river water now that permafrost has started melting with climate change. And then my last category is life. So the resolving power of ion cyclotron resonance, this is the competing technique. This is the mass. This is a time of flight measurement. And you've got these 4 metabolites. These are products of metabolism in your body. These are molecules, small molecules that your body uses to process energy so that you can live. Well, if you look at these masses, they're too close together. With the ion cyclotron resonance, you can easily resolve these 4 metabolites, whereas the old technique can't even begin to do the job. Well, you can also make an image. There's a lot of words. I'm running a little bit low on time, so I'm just going to focus on the key thing. Assume that this is a piece of tissue. So what you'll do is you'll focus a laser on one point in the tissue. The molecules are released from that location on the tissue, and you use our technique to identify what are those compounds, what are those chemicals that are coming off of the material at that point in the tissue. Then you move to the next point in the tissue, and you shine the laser, and you see what comes off from that part of the tissue. And you're able to make images of the mouse brain where you're looking at just where is one particular chemical in the mouse brain. So on the left, or on the right, is a common monounsaturated lipid. A lipid is just a fatty molecule that doesn't dissolve in water. They're used to store energy or to send signals throughout the brain. And on the left is an omega-6 fatty acid that has important neurological function. So doctors will be able to go eventually, when we do this on humans, we'll be able to go in and see where is this neurological function compromised because it doesn't have the right balance of chemicals in that particular part of the brain. So we're making images of the brain with 1 micron resolution, chemical by chemical, by measuring the mass of these chemicals. We can use a technique called nuclear magnetic resonance, where we're looking for active compounds like pharmaceuticals that have been created by natural evolution. So a walking stick can spray venom up to 40 centimeters in any direction. It temporarily blinds its predators. And before the mag lab, a grad student would purify 10,000 milkings to get enough of a sample to analyze the venom. Can you imagine you show up your first day in graduate school, professor, what do you want me to do? And the answer is start by milking 10,000 walking sticks. Well, it turns out that we've developed a coil out of high temperature superconductor to improve the sensitivity by 4 orders of magnitude. You can now analyze the venom from a single insect, from a single milking. The total sample is only 0.1 millimeters on a side. Incredibly small sample. And we're able to determine what was the chemical that this walking stick is using. And we're able to study an insect as it ages. We're able to study as it moves. We're able to study how its venom changes if it's under stress. So you get much better understanding of what's going on. There were some scientists who noticed that there was a mollusk that lived on the Great Barrier Reef and it had no shell. How does that survive? It cannot run away to save itself. It cannot bite or claw in self-defense. So it pretty much relies on chemical warfare. It's exuding chemicals that make it so nothing wants to eat this. Well, they collected a sample in the previous millennium, the 1900s. They were able to analyze it in 2009. And instead of chemical warfare, in the paper they called it an extraordinary group of bioactive natural products, which is fancy words for chemical warfare. And they have a pretty complex molecule they found, and this one kills fungus. And so this protects this animal here from fungus. And one of the problems with global warming, you may not know, we're worried that fungal diseases would become a much bigger problem, because the chief way you fight fungal diseases now is you run a fever. But what if the average temperature goes up by 5C? Then the fungus are going to evolve to survive at higher temperatures. So when you run a fever, that fungus may not care. So we want to understand as much as we can about how materials in the natural world are fighting fungal diseases. All right, we've got a magnet I told you about on the first slide that goes to 21 Tesla to do MRI on mice, 10 to 20 times more powerful than the magnets that doctors now use. So we can make high definition pictures. We can even see individual cells, not just organs, but individual cells. 30 years ago, the record was a frog egg. Okay, we started with a big individual cell. It's a millimeter across. But now we're looking at individual neurons, 10 microns in size. We're also starting to look at sodium. And every MRI you've seen that doctors use is imaging the hydrogen in your body. And hydrogen gives the biggest signal. It's also the most abundant element in your body. So it's the wonderful way to see what's inside your body because hydrogen is everywhere. But we're looking at sodium here. Why would we do that? It's a much smaller signal. There's only 1/1000 the abundance. There's 1,000 times less sodium in your body than hydrogen. And the reason is because you're not just water and fat. Most of your body's water, most of the rest of it's fat, I'm sorry to say, but that includes this part up here. So hydrogen is great if you want sharp images. If you want a really blurry image, look at sodium. Why are we willing to put up with such a bad image? Well, dying cells absorb sodium. Nobody knows why, but we don't need to know why. So at the magnet lab, they said, let's use this. This mouse has a tumor right there in its brain. Chemotherapy, you may know, attacks your immune system. So after you've had several chemotherapies, you can't have any more. In fact, my dad passed from cancer eventually because they gave so much chemotherapy, they just couldn't do it anymore. The chemotherapy would have killed him. So here they just give a little taste of chemotherapy treatment A to see if that's going to work. But it's so small that it doesn't damage the immune system. If nothing happens, they'll give it chemotherapy treatment B, and then they'll image just 4 days later. If the tumor is lighting up, they know there's a clear indication that this chemotherapy will work. So in the future, you may be able to get the right chemotherapy the first time every time. Now, we're not ready to do this on humans because our magnet only has a hole this big in the center, and if you try to put a human being inside of that, you run into other medical problems. But we're doing the groundbreaking research on mice and rats. Well, somebody said, if you can look at sodium, let's look at lithium. So we're now doing magnetic resonance imaging on lithium batteries. So we're studying batteries without the need for exploratory surgery or an autopsy after the battery's dead. So you may know the discharge-recharge cycle of lithium batteries is not perfect. The battery grows lithium filaments on the electrodes. And you've all had the experience where a lithium battery works very well, very well, very well, and then it won't hold a charge. That's when those filaments touch. And so you can no longer use that battery. Well, we'd like to image those filaments without cutting the battery open. So this is an uncharged lithium battery. This is the charged lithium battery, where we're starting to take magnetic resonance images of the lithium battery without cutting it open to explore to see what's happening inside. All right, there's one example, my final example, where we merge materials and life. Stem cells have been labeled with nanoparticles that show up in MRI images, in magnetic resonance images. We're using these magnetic quantum dots that go into stem cells to watch the brain heal itself. This is an actual image of a living mouse brain made using MRI, and what we're seeing in blue are the stem cells that have responded to the brain damage that resulted from a stroke. We don't know how those stem cells know where to go, but we can now see them and watch them as they move to new places. These are the exact words I used at the beginning. We talked about tuning electron interactions and probing quantum phases in the superconductors. the vector orientation in that Lazarus superconductor, measuring molecular masses in oil, in biofuels, in metabolites, manipulating nuclear spins, that was the part about the insect venom, and getting information on biological compounds and magnetic resonance imaging. Thank you very much for your attention. I'd be happy to answer any questions. Ran a little bit long, I'm sorry for that. And we're going to get some questions from younger people too, so it's not just going to be the old people. Not that you're old.
Thank you for your nice talk. I want to ask you about what do you consider that are the main challenges in the creation of magnetic fields in the next years?
So the biggest frontier is developing high temperature superconductors to the next stage. You know, those curves were almost horizontal, and there was no big gray-haired guy saying you have to stop here. What we're doing now is we're designing, we achieved already a leap from 24 to 32 Tesla. We're designing a 40 Tesla all superconducting magnet. So we have to figure out how do we make sure the quality control is good enough, because now the magnet's getting big. So if there's one mistake, that's a problem. We have to handle the forces. But we don't see a limit yet to what high temperature superconducting magnets do. Once we get this 40 Tesla magnet, knock on wood, we hope to combine it with a resistive magnet, because that's a tried and true technology, to get to 60 Tesla DC. So the biggest, there are many frontiers in magnet technology. In my mind, the biggest and most exciting right now is continuing to harness that rapid improvement in high temperature superconducting technologies.
Okay, thank you very much indeed, first of all. I have a curious question. While you were explaining the board part, I disagree. You told us that there is a magnetic resistance when with the plots that had a very straight line zone. I would like to ask you if you could tell us more about that. You mentioned during the chart, please.
So you're asking about, it's a long talk.
Yeah.
You're asking about this linear in T. Well, here we go. This linear in T.
Yes.
Can I explain or tell any more about why that happens? No. It's a mystery, and even when there's been a breakthrough in the last year where physicists who study condensed matter physics have gotten together with physicists who study black holes, because the thinking is that this is evidence that you don't have individual electrons anymore. In quantum mechanics, every electron is identical and they're always exchanging with each other. And if they exchange, they become entangled. Black holes, one of the exciting things of black holes is that they're maximally entangled. And they think that this is evidence that you don't have electrons that are recognizable as individual particles anymore. You have a very entangled quantum mechanical system. So there are now theorists from condensed matter physics going to the same conferences as theorists who work on black holes because they think it's the same physics. What happens in quantum mechanics when you don't just have two electrons that exchange? We studied that back in the 1930s, and there's still very exciting results from that. But what happens if the billions and trillions and quadrillions of electrons, and there are many more than that, are all exchanging with each other? And that seems to be how we understand black holes. And our guys said, well, we have something weird going on here that doesn't look like electrons. Maybe it's the same thing. Now, I try to read those papers. I try to listen to those talks. And do I understand any of it? No. Other than what I just said. Yes?
Hi, Greg. I come from the biophysics side.
That's okay.
And thank you. And specifically, talking about the mass spectroscopy.
Yes.
I mean, it's very exciting because you get a whole spectrum of molecules being identified. How does it compare with traditional mass spec that runs in the chemistry labs in terms of resolution or? And
Right.
I have a second question: do you quantify the amounts of molecules that are in your sample?
Those are good questions. I'll take the second one first, and then you'll remind me what the first one was. Getting the total quantity is not as easy. I'm told it's not simply the area under this peak. So getting the exact quantity is apparently a difficult thing to do with this. However, the resolution, we can get 100 parts per billion. I don't know what the conventional mass spectrometers can do, but I have the impression that that's 1,000 times better. The best you can do is this time of flight that I showed, where it's a quadrupolar time of flight, whatever that means. There you can see the resolution is, and we've now gotten much better than this. Those images I showed you of the mouse brain of the two molecules, those were both within the width of that peak. So we're getting resolutions like this, whereas the time of flight is about that. So it's at least 50 times better or 100 times better. But there's another advantage. As we go to higher fields, we can go to heavier molecules. The conventional compounds will start to fail after a few hundred Daltons. We are now up to the point where we can go up to thousands of Daltons, which means that we can look at the proteome of the human being. So look at all the proteins in the human body, and 95% of them are within our accessible range of masses. So they are starting to now, instead of trying to study the proteins in the body by cutting them into pieces and then trying to figure out how they were put together in the first place, because you have to cut them into pieces to have the analytical tools work. We now, by going to 21 Tesla, don't have to cut up the proteins in advance. It's called top-down proteomics. And that's a huge field that's taking off. We're going to be able to start studying what happens when the brain is diseased and metabolism isn't working properly because the wrong chemicals are showing up in the wrong places. The sky is the limit in that area. It's really exciting.
That research happens at Florida State.
Everything I've shown happened, yes, that research happens at Florida State. All of the ion cyclotron resonance is at Florida State. We hired one of the co-inventors, and then he and his team went to further develop higher and higher fields.
Thank you.
Yep. Is there a question from a student? There we go. There's one here, one over there.
Hi, it was a pleasure meeting you.
Thank you.
When you mentioned the mysteries of superconductivity, what would you consider like the future of humanity if we find a solution or an answer to them?
So that's a good question. So it's a difficult question to answer because the engineers are being able to make uses for high temperature superconductors to make powerful magnets. They're being used in some of the big wind turbines to generate clean power from wind already. They're being used in other areas as well, the accelerators that are used as atom smashers. So if the engineers can do all of that without the physicists understanding why it superconducts in the first place, maybe we don't need an understanding. However, once you get an understanding, it always has so many other applications because it opens your eyes to everything else. So low temperature superconductivity was discovered in 1911. The theory, which is called BCS, John Bardeen, Leon Cooper, you heard of Cooper pairs in the talk, and Bob Schrieffer, who was the first chief scientist at the National Magnet Lab, together came up with a theory in 1957 that explained low temperature superconductivity. So it took 46 years. That theory is so applicable throughout physics It's been used in every other field of physics. High energy physicists use it, nuclear physicists use it, cosmologists use it. It's a generic description of how electrons pair up, or two fermions, to use a technical term, pair up with the help of a different kind of particle called a boson. I know this is jargon, but the point is that a theory that applies in one place, like he left, like black holes, may actually apply somewhere else, like high temperature superconductors. The low temperature superconductor theory has applied all across physics. Many of us believe that the solution of high temperature superconductivity will enable us to understand what we call strongly interacting systems, where the electrons are so interacting that they become difficult to distinguish. So we expect huge strides in academic understanding if we can solve high temperature superconductivity. It's possible that then some engineers will say, well, if that's the reason it works, we can now design a better high temperature superconductor. If we can make a superconductor at room temperature without applying a massive amount of pressure, there are superconductors that superconduct very close to room temperature, not room temperature here, but room temperature in Siberia, but they're under massive pressure, so they're not useful. But if we can make a superconductor that works at room temperature, one of the first things we'll do is we'll replace the power cables that run electrical power from the generation to where it's being used, because we waste 10 to 15% of all the electricity generated by heating up the world's largest toaster. That's all we're doing, is we're heating up the air around those wires. If we could use superconductors, then we could save all that energy, 15% in one fell swoop. That's just one application.
Okay, thank you.
Levitation might become something that's no longer exciting to see. You know, when CDs, how many people still remember what CDs are? When CDs came out, people like him used to hang them from the mirrors of their car because it was really cool, because you get rainbows. Well, that was something scientifically that was known. You put scratches that are evenly spaced close to the wavelength of light and you get rainbows. But it had never been seen in every day. So that was really cool. Well, we do demonstrations in the laboratory where we levitate magnets above superconductors, but it has to be cold. It has to be at liquid nitrogen temperatures. Well, if superconductors superconduct at room temperature, levitation may not be that exciting for your grandchildren.
Okay. Hi, Greg. First of all, thank you so much to be here with us. My question is, we learn about a lot of discoveries from the high magnetic field laboratory, from maybe biological applications or medical as well. The question is there any chance to use the high magnetic fields to maybe manipulate or even improve the process in the nuclear fusion reactors, like ITER?
Yes. So ITER is, for those who don't know, is the largest experiment in the world that's trying to fuse hydrogen atoms together to form helium, which is a different way of generating nuclear energy that's cleaner than what we do now, which is to split apart uranium atoms, which creates radioactivity. So a fusion experiment would be, that's successful, would be a source of clean energy. And ITER is the biggest experiment in the world. However, $250 million of venture capital money has gone into one company alone, Commonwealth Fusion in Massachusetts, seeking to use high temperature superconductors because you can make smaller, powerful magnets, and the only way that a fusion machine works is to confine the hot plasma with magnetic fields. So they're doing a $250 million bet that they can do fusion with a much smaller machine using high temperature superconductors. They're not the only company that's doing that. They seem to be out in front. We're being recorded, aren't we? They're not talking about much of what they're doing. And they were very excited about an upcoming test that occurred in the spring. And we've not heard a whole lot about the results of that test. So I'm thinking that they're scratching their heads and have run into a bit of a problem. That's what progress looks like. But there are people who are investing large amounts of money into advancing fusion through the use of high temperature superconductors.
Thank you so much.
Hi, my question is about the application in medical physics with the images that you can generate in the MATLAB. It's about the possible to use it in the human brain for specific the Alzheimer disease.
For specific, say again?
The Alzheimer disease, you can the size. Sorry.
Alzheimer's. Okay.
Alzheimer. Yeah.
Thank you.
You can use nanotechnology to restrict the beta amyloid, but you say that you can only use that in mouses for the
Right. So if you want to do imaging in human beings, if you're in a clinical environment with a doctor, you're typically up to about 3 Tesla now. If you're in a research environment, there are magnets that are 7 Tesla and some that are 11 Tesla that have been approved for research on human beings. So they have a bore size that's big enough to fit most human beings, perhaps not me, to do magnetic resonance imaging. To date, there's no known limit of magnetic field where you start to damage the brain or damage the human body. DC magnetic fields seem to have no negative impact on the body. But changing magnetic fields do. So if the magnet is sitting at field and the patient is coming closer, the patient is experiencing a changing magnetic field. So one of the effects is you see flashes in your eyes, and they're worried about the electrical currents that get induced, and can that cause problems. So there is a frontier that's somewhere between 3 and 11 Tesla for working on humans. There is work being done trying to image the plaques on that are created or at least are correlated with Alzheimer's. We're not sure if it's a cause and effect, as I understand the science, to try to get these kinds of image on those sorts of chemicals as well. We're also using our ability to identify different metabolites and different brain chemicals to try to look for the aggregation as well. There's an application on using pulsed magnets, because pulsed magnetic fields can actually relieve pain. So the conduction along your nerves is not because of electrons going along your nerves. They don't work like copper wire. In fact, it's because ions go in and out of your nerve cell walls. So it's like a rope. I can snap a rope and you'll see the wave go down the rope, but any part of the rope is going up or down. No part of the rope is heading towards the wall. That's how your nerves work. Well, pulsed magnets can keep those ions from going in and out of the nerve cells and relieve pain. Pulsed magnets can also, if they're applied to this part of your brain, relieve depression for reasons that aren't really understood. So they take a pulsed magnet here, and this is your motor cortex, and it'll cause, it's the left side of your brain, so it controls the right side of your body. It'll cause this thumb to jump. And then they'll move forward to a part of the brain where very deep in the brain, there's something that's linked with depression. And pulsing repetitively, day after day after day for 20 minutes, can relieve suicidal thoughts. And I know that because not only did I once hold the world record for generating magnetic fields, I'm also bipolar. And I've had that done to my brain. So I not only design and build and use, but I apply pulse magnets to my brain. And it's amazing that over the course of weeks, it just lifts your mood. So it's clear that magnetic fields have many roles to play in brain function, in brain health, and treating disorders of the brain.
Good afternoon. First, thank you to be here.
Thanks.
I was wondering about the temperature. Well, you was talking about Kelvin.
Yes.
Temperatures under 50 Kelvin.
Yes.
And how is it possible? How do you get that information?
So just for people who may not know, the scientific temperature scale is Kelvin, because 0 is absolute 0. Temperature is nothing more than random motion of particles. So if you were to approach absolute 0, you can never quite get there. The atoms just slow down, and eventually at absolute 0, they would not be moving at all, no vibrations at all. Room temperature is 300 Kelvin. So how can you measure temperature all the way down to 50 Kelvin, or indeed much colder than that? The easiest thing to do is, well, at 50 Kelvin, am I an expert? You can use resistors that become more and more resistive as the temperature goes down, because the electrons sort of get frozen out. And those can be calibrated very nicely against helium gas that's flowing. When you get down to 4 Kelvin, you can actually measure the pressure of the helium down to about 1 Kelvin as you pump on the helium. If you want to go below 1 Kelvin, you can use helium-3, which just has 1 fewer neutron, and it's easier to pump on that. You can pump that down to 0.25 Kelvin. So there are actually many ways, and it can be as simple as measuring a resistor to determine temperature.
Okay, thank you.
Yep.
Good afternoon, and thank you for this. I was wondering, as soon as you talk about that, I thought this was a type of therapy about in brain and that's Alzheimer and that type of things. In that same way, it will have other implications in the pharmaceutical industry.
Yes.
As in other parts of the body, I mean, in other diseases.
Yes.
I mean, like not only at the neurological level,
Yes.
in other levels, there it could be applied this type of therapist. I mean,
So I didn't get the nature of the question. What's the specific question?
I mean, this in general, the magnetic fields could be used in another way, like a type of therapy.
Right.
In ways like I don't know, vascular levels or something like that, more than neurological.
Right. So you're describing other frontiers, I think, rather than being neurological, which is often sort of electronic in nature. Are there things that are more interested in pharmaceuticals? So chemical interactions. Yeah, there's quite a bit of research. So I talked about the venom of the walking stick and the antifungal compound in the mollusk on the Great Barrier Reef. There are thousands of studies going on trying to look in the natural world where there's been 3 billion years of evolution. What has evolution discovered? One of the leading cancer drugs is called Taxol. It comes from the bark of a tree. And so it was discovered in nature. I forget which tree offhand. And then they learned that that is protecting the tree. They learned that it's effective against cancers, certain cancers. And so then they learned to synthesize that pharmaceutical in the laboratory. That's actually the single invention, most valuable invention in the history of our university. It made several $100 million for the university, the discovery of how to make Taxol. So there are plenty of frontiers that are studying the chemistry that might be pharmaceuticals, the chemistry that's going wrong that tells you there's a disease that's happening. Even the ion cyclotron resonance. I said you can analyze petroleum or river water or asphalt, or here you image chemically specific parts of the brain. You can also look at urine or cerebrospinal fluid. and identify every molecule that's in that fluid from your body. Many tests that doctors do, when they have you pee in the bottle, it's not just to test your aim. It's to see, are there chemicals in the urine that indicate your body is trying to fight a specific disease? Well, with this technique, we may be able to look for thousands of different signs that there's a disease going on in your body. So it's not just therapies, it's not just neurological or pharmaceutical, it's in detecting diseases as well. So there are frontiers in every direction you look. All right.
Great. Thank you very much for being here with us in this great talk. And we invite you to talk with Greg. We have a small get-together. So, debería estar hablando en español, ¿cierto? Vamos a tener una sesión con un poquito de vino y quesos acá afuera. Sí, entonces vamos a tener esta sesión acá afuera. Hay una serie de pósters que hablan más en detalle de algunos ejemplos del MagLab. Y al fondo de ese pasillo está siguiendo el pasillo, está el vino y ahí vamos a estar compartiendo un tiempo juntos. Mañana están bienvenidos al IP 101, o sea, el edificio de física, en una de las salas de reuniones. Va a haber un espacio de preguntas y respuestas con Greg, por si tienen alguna duda específica que quieran preguntar. Es
2
a las
p.m.
2 p.m. en el edificio de física de aquí de la Universidad de los Andes.
IP
Para ingreso, entonces, yo creo que para ingreso se puede llamar a la Secretaría de Física si no tienen ingreso en este momento y les podemos dar el ingreso antes del evento. Gracias. Entonces, muchas. Thank you, Greg. It's been fantastic.
Le recordamos al público asistente no